Hi everybody, I'm going to talk about integration in proton NMR in this video. So the integration is really talking about how many protons are making up each peak in your NMR spectrum. So it is also determined by finding literally the integral. So we're looking at the mathematical definition of integral, which is the area under the curve. And it's comparing that area to the other areas of the other peaks. And then it compares them in a ratio. Okay. So if we're looking at our kind of summary NMR that we've been pulling out for the last couple of videos, if we're looking at that, the integration number is found right here. Okay. So integration. So it's a super handy piece of information because it tells us how many protons are in that unique environment, which is really, really helpful information to have. So if we look at a couple of examples here, this very much comes down to being able to identify your equivalent proton environments, because that's going to depend on how many protons are in that environment, okay? Which is what our integration is telling us. So if we think about drawing in our protons here, it's a similar type of structure that I had set up for a previous, um, that I used in a previous video. But when we're looking at all of the H's here, this CH3 is not the same as that CH2 because I don't have a plane of symmetry there. But if we're looking at these methyl groups on the side, we've got 3 methyl groups on the same carbon. They're in constant rotation, and these are all going to show up the same. Okay. Also, all of the H's in each methyl group are going to show up the same. So when we're looking at this, all of these H's are going to be one group. Then these H's the second group, and these H's the third group. Okay. But again, it depends on the equivalent protons. So if you're not feeling good with that, do some practice, rewatch that video, come to help hours and ask some questions. If we look at this example, so this is one where we do have a plane of symmetry right here. Okay, so we're kind of looking at the same equivalent proton type situation here. And keeping in mind that if I've got this as one environment, I have a mirrored environment over here. So we're looking at A over there. I have this methyl, and all 3 of those H's are going to be the same. And those are both going to be the same environment as well. So if I'm looking at my integration ratio, I am going to be seeing all of these protons showing up in my integral for A. So meaning that my A peak is going to be a very large peak, right? If we're looking at integrations, we're thinking about area under the curve. It is going to be a large peak. So A is going to have 9 protons in it. Okay. B has 2 protons and C has 3. Okay. If I'm looking at this one on the other side, my A position has 1, 2, 3, 4. And my B has 6. Okay. So what's important to note here is that because it is a ratio, it might be presented to you slightly differently, right? So if I have 4 and 6, the other way I could have labeled that was 2 and 3. Because they are showing up in a 2 to 3 ratio of those integrations. So make sure that when you're looking at your NMRs, you want to be kind of taking into account that the numbers that you're seeing might actually be double what they actually are, to account for some of that ratio and kind of, you know, showing the ratio as the smallest possible version of it. And keep an eye out on that, and that thinking about that we might have a mirroring situation where it's actually double what it shows. So when you're looking at integrations on an NMR spectrum, you're going to be looking at that x-axis, which is our chemical shift. It's going to have peaks popping up on it. The integrations, depending on where you're finding the NMRs, could be listed in a variety of different places. So sometimes you've got integrations that are listed down here, being very, very careful that you're not confusing them with the ppm, okay? The integrals are going to have usually some type of bracket and a number, and not to be confused with the number of the x-axis, which is the ppm. Okay, other places might show it on top of the peak, where it's just a number kind of on top of the peak, showing it as the integration. And then some situations are going to actually give you an integral line, okay? Because kind of more olden days, what they used to do is they used to provide those integral lines, which could literally be measured, and then that ratio could be devised from that. So definitely different options, but generally if you see a number that has brackets on it, or a number above a peak, it's typically going to be the integration that you're looking at, where the ppm is going to have like, this 0 and then 1, 2, 3. And it's hopefully going to be fairly clear. Okay, dot, dot, dot. But making sure that you're not just looking at any of those x-axis values for your integrals. That is not it. Look for the brackets. Okay, so because those integration values are ratio based, most of the time the analyzed NMRs that you'll be given will match the integration values for the number of hydrogens. Okay, so for example, if I'm looking at ethyl acetate here, I've got A, B, and C proton environments, and A has 3 H's in it, B has 2 H's, and C has 3 H's. So if I'm looking at that, I'm typically going to be seeing like, okay, there's the 2, there's the 3, there's the 3. That's most of what you're going to see. That's in a processed situation where somebody has gone through and integrated that and then done a little bit of processing, a little bit of thinking of their own to make sure that they're saying, okay, this should be a 2 and then a 3 and a 3, rather than saying this should be a 1 and a 1.5 and 1.5. Okay, because that's the kind of ratio that you could be ending up with. And obviously we can't have half of a hydrogen in an environment. So we are looking at whole numbers here. If you're given something that has minimal processing, okay, so this is our minimal processing situation. Sometimes they might be raw integrals that are just comparing the area under each peak. So it's just spitting out some numbers that are equivalent to the area of that peak. So in that case, you do need to do a little bit of conversion yourself to get somewhere useful with your integrations. Okay, so find your lowest integral and then assume that that's going to be 1 hydrogen. Then you can divide all your integration values by that lowest integral. And if that answer, if that quotient is roughly whole numbers, you've probably got it, okay? If it has decimal places, like 0.5 H's, again, we can't have half of a hydrogen, then try doubling all of those quotient values to get to whole numbers. It's usually going to be enough to get you there at that point, but you can do more like ×3 and ×4 if you need to. It's usually not going to be something that you need to do. So for a couple of examples here, if we look at this example where it's got some integration values down here, keeping in mind that when we're looking at our chemical shift, our ppm is these numbers. And then our integration values, again, are shown with those brackets and given different numbers besides the ppm. So just be careful when you're looking at that. It's easy to get those things mixed up. So my lowest is going to be the 9.1. So I'm going to set this equal to 1 hydrogen. Okay. And then if I take all my others and divide it by that 9.1, so I'm going to label this A, B, C, D. Okay, where I'm setting D as 9.1 equal to 1 hydrogen. So for A, I got 45.1 divided by 9.1. And that is 4.96. B is going to be 18.6 divided by 9.1. Which is 2.04. C, 19.1 divided by 9.1. 2.10. And then D, we said 9.1. Oops. Divided by 9.1 is 1. Okay. So we can start to see that our ratios here are starting to come out with those quotients being pretty much whole numbers, where we would just round that 4.96 to 5, the 2.04 to 2, 2.1 to 2, and the 1 obviously is 1. So we could be looking at this as an integration of 5 H's, 2 H's, 2 H's, and 1 H. Okay, so that's going to give you those integration values that are actually going to be helpful, where it's saying I have 2 hydrogens in this environment rather than something rather nonsensical like 18.6, which doesn't really give you any context. Okay, so if we look at another example here, again, we're looking for the smallest. So I'm going to go pick this 13.9 over here, and I'm going to set that equal to 1H. The equal sign on the wrong side. Okay, so I have A, B, C, and D. So A is 13.9 divided by 13.9, and we said that that was going to be 1. B has 21.5 divided by 13.9 is 1.55. So we're automatically coming into some issues here where it's not quite as close, right? The other ones were all very, very close to their whole numbers, so we can round it without any kind of issues. But we're seeing that we definitely have some problems with that with this one. Okay, so we've got 2 that are in that 1.5. We've got half a proton type situation, which is not going to be super helpful here. But what we can do is we can just say all of these times 2. Obviously, did not scale it out right. Okay. Okay, so if I go times 2, that's going to leave me with 2, 3, 2, and 3. So if I have 2, 3, 2, 3, those are starting to get to much more reasonable proton integration values. And then we can see if that makes sense. As you're putting things together, you might need to be adjusting this if you had to do this process of kind of getting to your own proton integration values. But overall, it's going to be very, very helpful here to be able to get these, because this is what helps tell you whether or not you've got a CH, a CH2, or a CH3, and how many of those are in the same environment. So it's really, really powerful information, especially when it comes to building our fragments, which is going to come in another video. All right, so let me know if you have any questions. Again, those integrations are protons in the environment. Super handy information. Don't pass it by.